All right, everybody, we're going to go over the electrical pathway of the heart, so the electrical conduction of the heart and the action potentials with the pacemaker cells and the myocytes. We're going to go over all the steps of how those action potentials work, and we're also just going to go through the electrical conduction pathway of the heart here. Okay, so we start out, we have our heart, we have our SA node and our AV node. Okay, the SA node is the node that is going to spontaneously depolarize. So it doesn't need a signal to tell it to depolarize. It's just going to spontaneously do it. So it's the SA node and the AV node that are going to follow this pathway of the action potentials. All right, so the first step in the electrical conduction is the SA node spontaneously depolarizes by funny channels opening up on the membranes, on the cell membrane, allowing for slow influx of sodium to come into the SA node. Then once we hit threshold, those funny channels are going to close and voltage-gated calcium channels are going to open up. And then calcium is going to flow into the cell, causing this depolarization that you see right here. Then once we get to the top, we have those voltage-gated calcium channels closing and voltage-gated potassium channels opening, allowing for potassium efflux out of the cell, which causes repolarization. And what you see right here with this first phase of the graph is called the pacemaker potential. Okay, so the SA node does its action potential, it goes off, and once the SA node does the action potential, that causes the left and the right atrias to contract and then send blood down to the respective ventricles. So once the SA node goes through its action potential, it spreads its signal all throughout the atrias, including to the other side, causing the atrias to contract, which then pumps the blood down to the respective ventricles. Once that is completed, then the SA node sends the signal to the AV node through what's called the internodal pathway between these two. Again, that's the internodal pathway. And the AV node goes through the exact same action potential graph that you see right here with all the same steps. Now we have with the contractile cells, aka the myocytes, they're going to follow a different action potential pathway. And the way that these guys work is you have your resting membrane potential, which does exist because you don't have you need to wait for the signal to depolarize, whereas these guys, the SA node spontaneously does it. This is still going to follow the resting membrane potential rule. This sharp increase that you see here is where voltage-gated sodium channels open, which causes rapid influx of sodium into those myocytes. Then you get to what's called the plateau phase. Now the plateau phase is when the voltage-gated channels that were previously open close, and then voltage-gated potassium channels open, and slow voltage-gated calcium channels also open at the same time, causing calcium influx and potassium efflux. The potassium efflux matches the calcium influx, which is why you have this plateau phase. And this plateau phase is where contraction of those myocytes occur, where the myocytes will follow the same sliding filament model as the skeletal muscle does. Then once you get to the decline here, you have those voltage-gated calcium channels completely closing up, and then the voltage-gated potassium channels remain open, causing potassium efflux out of the cell. Then you have the sodium-potassium pump reestablishing that resting membrane potential, as it always does with all cells. So another thing we need to note is that myocytes and all the heart contractile cells work in what's called a functional syncytium, where everything is connected through gap junctions. Okay. You also have desmosomes, which provide mechanical strength, preventing myocytes from ripping apart. And you have these gap junctions, which allows for signals to travel through all of the cells, making for one fully coordinated tissue where all of the myocytes contract at the same time. So as this is happening, you have the SA node releasing its signal, and there's myocytes literally everywhere where there's not these red dots. So it spreads the signal to those myocytes in the atrias, causing atrias to contract, pump their blood to the ventricles. And then once you hit the AV node sends signals down through what's called the interventricular septum, which is this section of the heart right here. It's going to send the signals to the ventricles, causing the ventricles to contract. And again, it's just, there's nerves running all through here, connecting to these ventricles. Again, these are all myocytes in here, which connect to the ventricles, causing the ventricles to contract and pump their blood out the pulmonary trunk and out the aorta. It's out the pulmonary trunk if you're talking about the pulmonary circuit, and out the aorta if you're talking about the systemic circuit.